Hi, good morning. Today we are going to discuss about some important topics like the right and left coset of a subgroup and about an important theorem which is known as Lagrange's theorem. So we start with a group G together with a binary operation set dot defined on G, and uh, let's consider a subgroup H of G together with the same binary operation star. Now we define the left coset of H in G as AH, notation is AH, and is given by set of all A dot H, where H is an element of the subgroup H, and A is an arbitrary element of G. So for any A belongs to G. For any A belongs to G, we can define the left coset AH as the set of all A dot H where H belongs to capital H. And in a similar way, we can define the right coset as the HA, and which is a set of all HA where H belongs to capital H. So that's the concept of left coset and right coset. So as an example, let's consider the set of all real numbers together with addition is a group. Now consider the subset of R, uh, the set of all integers, and set of all integers together with addition will also form a group. Now, let's take an arbitrary element A belongs to R. So for simplicity, let's take an element of R which is not in Z. Say something like A is equal to root of 2. Now, the left coset AH, or here in this particular case, it is A Z is equal to set of all A, here the operation is addition, A plus Z uh, or A plus Z, such that Z belongs to A plus Z, where Z belongs to capital Z. Or in another way, capital Z contains the elements like 0, 1, 2, 3, etc., and minus 1, minus 2, etc., from minus infinity to plus infinity, and the that is Z, and the left coset root 2 plus Z or root 2 Z is nothing but minus 2 plus root 2, minus 1 plus root 2, 0 plus root 2, 1 plus root of 2, 2 plus root of 2, etc. This will be the uh, left coset, and in a similar way we can define the right coset also. So that's the concept of left and right coset of a subgroup in a group. Now let us go to the statement of Lagrange's theorem. Lagrange's theorem. The theorem says that if G is a finite group, so we will give the most simple form of Lagrange's theorem. If G is a finite group and H is a subgroup of G, then order of H divides order of G. So by the time order of H it can be simply understand the concept of order of H as the number of elements in H, and order of G is the number of elements in the group G. And if H is a subgroup of G, then the number of elements in H divides the number of elements in G. So that's the statement of Lagrange's theorem. And in order to prove this Lagrange's theorem, we do it in uh, two steps. And first step, we prove a proposition which says the subset H and the left coset AH has the same number of elements. So they have the same number of elements. H and any left coset of H has the same number of elements. So for that, to prove this one, I define a function or a mapping from H to AH as phi of some element H is equal to AH, where this H belongs to capital H and A is an arbitrary element of the group G, or the underlying group G, and it is subgroup of G. Now, to prove that these two H and H have the same element, same number of elements, what we are going to prove is that phi is a bijection, or it is 1 1 and 1 2 mark. It's a 1 1 on 2 mark. If phi is a 1 1 on 2 mark, then obviously H and H have the same number of elements. So first we have to prove that it is 1 1, and in order to prove that it is 1 1, uh, we have to prove that phi of x or phi of x1 is equal to phi of x2 uh, implies x1 is equal to x2, implies x1 is equal to x2. What that is what we have to prove. And for that, if phi of x1 is equal to phi of x2, phi of x1 is equal to phi of x2 means phi of an element is AH. So it is A some H1 is equal to A H2. So that means if you pre-multiply with A inverse, uh, where A inverse is an element of G, then A inverse H1 is equal to A inverse H2, which means H1 is equal to H2. And H1 and H2 are two elements of H, and they are equal. That means if phi of x1 is equal to phi of x2, then that means x1 is equal to h2. So phi of okay. So here it is ax1. So let's write like this. Phi of h1 is equal to phi of h2 means h1 is equal to h2. That means it's a 1 1 mark. Then to prove that it is an onto mark, let's consider an arbitrary element of AH. So let's consider an arbitrary element of AH. Then that X is equal to A into some H1, where H1 belongs to capital H. Then naturally, uh, phi of H1 is equal to X. So for any element of AH, we have an inverse element in H, capital H. So what this implies is X belongs to AH implies there exists some H belongs to capital H such that f of H is equal to X. That means the function f or phi of h is equal to x. So that means the function phi is 1 1 and 1 2, and therefore the two elements, two sets h and ah have the same cardinality or same number of elements. So we can write order of h or number of elements in h and number of elements in ah and number of elements in HA are the same. Number of elements in right coset and the number of elements in left coset are the same. So that's our first result. And now let's consider a finite group G and a subgroup of G called H. Now, what we are going to prove is if if G1 and G2 belongs to G, then either G1H is equal to G2H or G1H intersection G2H is equal to the null set. That uh, what we are going to prove here is either two left cosets are the same or they contains no elements in common. So if you consider two cosets of H in G, either they are the same or they are entirely different. So that is what we have to prove, and to prove this statement we start with uh, the converse of our assumption, that is if possible G1H intersection G2H not equal to 5, and their intersection contains some element, and G1H is not equal to G2H. That is, we assume that if possible, the two left cosets are not the same, but the intersection contains some elements. So, if there is some element in G1H and G2H, then let's consider one among the common elements, and that can be written as G1 into some H1 since it belongs to G1H, and since it belongs to G2H, it can be written as G2 into some H2. H2 belongs to capital H. So that what we are doing is, if X is a common element in G1H and G2H, then X can be written as G1 into H1 since it belongs to G1H, and the same H can be written as G2H2 as it belongs to G2 capital H. So the common element can be written as G1H and G2H at the same time. And uh, let's consider G1 H1, and G1 H1 is equal to G2 H2, and G1. So here G1 H1 is equal to G2 H2 means G1 H1 into H1 inverse is equal to G2 H2 into H2 inverse. Uh, that means G1 dot the identity element H1 inverse is the identity element is equal to G2 into H2 H1 inverse. This is H1 inverse. So this elements H2 belongs to the group H, H1 belongs to the group H, H1 inverse is also an element of the group H. So H2 dot H1 inverse is also an element of group H. So G2 into an element of group H means this is an element of the left coset G2H. So what we obtained here is G1 into E is equal to G2H belongs to the left coset G2H. So if there is an element such that G1H1 is equal to G2H2, then G1 belongs to G2H. Now, let's consider the two cosets G1H and G2H, and take an arbitrary element from G1H. So let the arbitrary element be some x. Let x belongs to G1 capital H. And since it belongs to G1 capital H, it can be written as x can be written as G1 into some element of H. Some element of H, something like we already used the term H1, H2. So let us write it as some H3. X is equal to G1 H3 for some H3 belongs to capital H. And we know that G1 is an element of G2H. Since G1 belongs to G2H, this G1 can be written as G2 into some H4 where H4 belongs to capital H. So that means X can be written in the form G2 H4 dot H3, and that means X is equal to G3 G2 into H4 dot H3, and since H4 and H3 are elements of capital H, the group or the subgroup H4 dot H3 is again an element of capital H, say some H5. So X can be written as G2 into some H5, where this H5 is an element of capital H, and that means X belongs to the coset G2H. So if you take an arbitrary element from G1H, then you can prove that it belongs to G2H also. That means G1H is a subset of G2H, and we can use the same steps to prove that G2H is a subset of G1H, and by comparing these two, we can simply say that G1H is equal to G2H. But it's a contradiction since we assume that G1H is not equal to G2H and they have some elements in common at our starting point. But this contradiction is due to our wrong assumption that G1H and G2H have something in common. So that is wrong, which means G1H intersection G2H is equal to the null set. So that's our uh, result. So either if you have two left cosets, then either they are distinct or they have they are they are the same coset. So we just rewrite the statement of our last proposition. If G is a group and H is a subgroup, then if A is an arbitrary element of G, then A1H is equal to A2H, or A1H intersection A2H is equal to the null section. Now let's consider the group G, and this G can be written as, if G is a finite group, in particular if G is a finite group, then G can be written as the union of the left cosets. Say, take an arbitrary element from G and consider the left coset AH, or say A1H. Now, if it is our group G, then A1H is a subset of G, need not be a subgroup, but it's a subset of G, something like this. Now consider another arbitrary element of G, say A2, then find the subgroup A2H, subset A2H, or the left coset A2H, and then by our previous result, this A2H is either equal to A1H, or it is an entirely different subset of the group G. So if it is equal to A1H, then just ignore it and take another arbitrary element A3. And if it is an entirely different element, subset of G, then uh, write it here as A2H, then union A3H, etc. And since G is a finite group, we cannot proceed this process infinitely. It will end up at some particular stage, AKH. So G can be written as the union of a finite number of left cosets. And if you consider the number of elements in G, the order of G is equal to number of elements in A1H plus number of elements in A2H plus etc. number of elements in AKH. But we know that A1H, A2H, etc. contain the same number of elements, or by our first result, all the left cosets contain the same number of elements, and that is equal to the number of elements in H. So it is nothing but number of elements in H plus number of elements in H plus etc. number of elements in H k times, and therefore this is equal to k into number of elements in H, and k is an integer. So obviously order of G divided by order of H is equal to k, an integer, and that means order of H divides order of G. So that's our Lagrange's theorem, and uh, so the order of any subgroup divides the order of our group G. So that's the proof of Lagrange's theorem. So for the time being, that's enough, and